repeat tutorial series in Kerbal Space Program 0.90 Beta. In this episode, I start in the spaceplane hangar, not because we gotta spend too much time here. I want to get back to career mode and launch the mission to the moon. But first things first, I wanted to cover a part of the airplane basics episode that I sort of cut out of that episode, and I want to do it a little bit quicker than I originally did, so I'm not using the original segment I recorded. I'm actually doing it over again, and that's probably for the best. And so I've got this airplane built already because I wanted to get on with it, but a few things to note. First of all, you'll note that the landing gear is on these structural pylons that you can find here. Always nervous about using these. First of all, they're very heavy, mass of 0.2, and also they have emergency bolts, which is why they appear as decouplers here. Don't really need that because we don't envision dumping the landing gear there, but always worried about structural integrity with that. But we do need to extend the landing gear a little bit lower. They seem to be angled a little bit out. I'm not going to worry about that right now because if you've used these before, you know that selecting them is always a little bit tricky. Oh, I could select them there. Maybe... Oh, okay. Let me just leave them be for now. Alright, so you can see landing gear very close to center mass behind it, center of lift there. The first thing I wanted to talk about is a special kind of engine that's different from all the rest, and that is the Rapier engine. The Rapier engine goes in both modes. In other words, it has a jet mode and a rocket mode, which means first it starts out breathing in oxygen from the air so it doesn't have to carry it, but then you can turn it into a rocket so that uses onboard oxidizer instead of the external oxygen. So it can operate in the atmosphere efficiently and then operate outside of the atmosphere. Now, no rockets, of course, can operate in the atmosphere, but they don't have the benefit of sucking in the oxygen from the atmosphere, and these Rapiers do. Now, they have, well, I mean, they don't have too much drawback in terms of pretty much anything. They're a little bit underpowered on the jet side, and once you get into space, there are engines that are much better. You can see that the peak ISP here, the peak efficiency is 360 on the engine ISP right there. And so something like the LV909 has 390, which is much better. And even these guys have 370. So you're somewhat at a disadvantage once you get into space, but not a huge disadvantage. So it's a nifty little engine. You get it very late in the tech tree if you're doing career mode, so we wouldn't see these for a while, but you'll hear people talking about the Rapier engine, and so I wanted to mention that. It also has a drawback that it doesn't recharge your electric charge, I think, and so that's why one of the reasons I have solar panels up here, because otherwise we'd lose electric charge. You can see I'm using some of the interesting structural intakes here. Those are here. They're not as good as these shock cone intakes. They don't bring in as much air, but yeah, it looks better this way. And this is more of a looks plane. As usual, I design planes with as little wing as possible, and so this is probably going to barely make it off by the end of the runway. Now, the next thing I want to talk about is maneuvering, and there are three axes. Okay, in general, in 3 dimensions, you have 6 degrees of freedom. But with a plane, you only have 3 rotational degrees of freedom. And that is pitch, which is turning your nose up and down. Yaw, which is moving from side to side, rotating from side to side. And, of course, roll. Roll, which is, well, I'll just show them in practice. So pitch, yaw, and roll are the 3 that you have degrees of freedom you have. And of course you do have translational freedom in the forward direction, but that's about it. And that's just controlled by the thrust of the engines. In space you have all 6 degrees of freedom, and we'll talk about that. But so 3 ways of rotating a plane, and so that's what the various control surfaces are for. They are for controlling the plane in those 3 rotational degrees of freedom, and so we need to figure out which ones are to control what. The vertical stabilizers and their rudders, the control surface on a vertical stabilizer is the rudder, controls solely yaw, and that means it's controlling whether the nose gets turned left or right. If these little rudders are pointed to the left, if they're deflected to the left, the wind is going to hit them, and that is going to turn the tail to the right and turn the nose they're deflected to the right, the wind hits them, wants to push them to the left, which pushes the tail to the left, which pushes the nose to the right. You don't have to worry about all that, but you'll see it happen. Now, with these elevons, which is what they are on a delta wing. Now, you could have a horizontal stabilizer as well, and so there's more complex configurations than a delta wing. But I'll handle the delta wing first because it's a simple configuration. The downside of it is that it doesn't give you that much lift or pitch authority. But in general, these inboard ones control pitch and roll. Well, no, just pitch in general. But I tend to set them for roll as well because I like to have a lot of roll control. But in a real airplane, they wouldn't be used for roll. They'd just be used for pitch, which means putting the nose up or down. If they are deflected down, they'll tilt the nose up because of the wind being deflected by them. And otherwise, if you tilt them up, they will push the nose down. Okay, but I'm going to activate roll here. This too, I'm going to have pitch and roll, again, to maximize my pitch and roll authority, being able to make those rotations. And so, but mainly their job is to handle the roll. And what they do is one side deflects down and the other side deflects up. And that will produce the roll. So the side deflecting down, the wing will tilt up, and the side deflecting up, the wing will tilt down. And so if this side is down and this side is up, then what you're going to have is a roll towards the left, if you will. Okay, so let's get this dart underway and we can see all that in practice. And also, the one thing about the rapiers is, since they have two modes, what you're going to want to do is select them and have a switch mode. So this is an action group, and that means that when I press 1, it's going to do this thing. And I also want to set another one which will close these intakes, because we don't need the air intakes once we switch mode to rocket mode. So I'm going to have it close those intakes by pressing 2. You have up to 10. There are mods that extend to more action groups, but basically you can say what 1 to 10 does, and there are all sorts of things. You can see the cockpit has, you could toggle this so that if you press 3, it does a crew report. You can turn on the lights with it, and so all sorts of stuff like that. So you can just click parts. There's not much to do with the wings, but and the landing gear and all is already set to G, so no problem there. So yeah, but have fun with action groups. That's another important thing. But let's take this out, see if it flies, and just take a look at the 3 rotational degrees of freedom that I just talked about. Okay, so here we are. SAS on, throttle up. And so we're starting out in jet mode. You can see that by right-clicking on this. It has automatic switching here. I generally don't do that, but in this case, since I'm talking and trying to come up with stuff to say, I'll probably go with that. It's right now in air breathing mode, so that's good. And we have liquid fuel, and we also have tanks of liquid fuel and oxidizer here, just in case we want to go into rocket mode. Alright, here we go. Now this does not have that much lift or even pitch control, so I'm just gonna let it go very, very fast before starting to rotate. Alright, that should do. Okay, we're off the runway. Landing gear up. Alright. So now, pitch. You can see the control surfaces on the wing. Let's just get a pure controlling the pitch. Now, you do not want to deviate too much from your prograde vector, otherwise this thing will flip out. So you can see, as long as the prograde vector is following you, you're alright. And in this case, that's good. Let's get to a higher altitude. But roll. Now, you'll notice that once we're in a roll, the prograde vector starts moving down and to the right here in this case. So that's a natural tendency in roll, and that's because you're losing lift, because you have optimal lift when the wings are horizontal like because when you roll, you're tending to have your prograde vector go down, you'll generally want to pull up a bit while doing the roll, and so you're gonna turn quicker that way. But once again, you don't want your current direction, your angle of attack, to deviate too much from the prograde vector, otherwise you will spin out. The faster you're going, the more likely you're going to spin out, because the airflow is so intense over the wings. You can create a lot of disturbances, and that's much more so in real life than KSP. So here I'm going to turn. Again, I'm rolling and pulling up at the same time in order to increase the speed of the turn, and I'm going to buzz the island runway again. Okay, let's see how high we can get with this. Now, one saving grace of this particular design is it's got a lot of thrust considering its mass. Downside is that it's not really carrying enough fuel to get to orbit. But let's see if we can get to space. Okay, as we start getting higher, we want to gain as much velocity in jet mode as possible, and that's because rocket mode sucks in a lot more fuel and oxidizer, and we want to be moving as fast as possible before we make the switch. That way we'll have the best efficiency that we can get. Now, that'd be more important if we were trying to get to orbit. We're just trying to get to space here. Okay, the engines have automatically switched to rocket mode now. Closed cycle. They have less thrust in closed cycle than they do in jet mode, and they're overheating right now, so I'm going to throttle back. I'm also going to pitch up a bit, because we don't really need to worry about breathing in air. We just want to get through the atmosphere as quickly as possible. Okay. Let's see if that's enough to get us into space. 70 kilometers is space, but we're still in the atmosphere, so you can see it's producing a little bit of drag, pulling us back down. Now, we need to reserve fuel because we want to get back home. And in fact, in the lack of air here, I'm going to flip around. And prepare to go retrograde. So that we can slow down and head back home. As you can see. Looks like we need to, so I'm going to do a little bit of yaw to point properly here. It's actually not the aerodynamic controls that are controlling us right now. It's actually the torque in the pod, which is also using rotation. What the torque is so you see here you have toggle torque, and that's reaction wheels. What they do is they spin around, and because of conservation of angular momentum, the craft spins the opposite direction. So you've got these little discs that are spinning around at like 30,000 RPM, and in response, because the momentum has to be conserved, the craft itself has to actually turn the other way. But it turns a lot more slowly because, of course, it's much larger. Okay, we're in space. Let's retroburn. Okay, well, that's pretty much it for our oxidizer. Let's see, we're still in closed cycle. I'm gonna have the engines off, but switch to air breathing right now using the key 1, action group 1. Where are you, prograde vector? Let's go to chase plane view here. So we're sort of going like that. hard as I can anymore because I feel it coming back here. And we've got it. Alright. But we've got a long way to go back home. I'll probably cut most of this out because it's a long trip here. Unless something awful happens, of course. Okay, here we go. KSC is in sight. We're still going pretty fast. Actually, we're going very, very fast now. And that's partly because, of course, we've lost a lot of mass. We burned off all our fuel. Hopefully that means that our touchdown speed on landing is not going to be quite as high. Now, you can see I'm dropping my velocity because it's easier to maneuver at a lower speed. In fact, these little weird oscillations are partly because we're going so fast and trying to maneuver like this. With mod like Ferrum Aerospace, it becomes even more interesting to maneuver with an aircraft at high speeds, and in general I wouldn't advise it. So yeah, be careful with that. Now SAS itself, of course, is doing some of the pitch, roll, and yaw in order to keep me stable. Very helpful little thing. And actually, we can attribute that to Jeb now, I guess. Okay, gear down. And as always, verify that your landing gear is down. With a real aircraft, you wouldn't lower the landing gear at this kind of speed, but we do not have to worry about that in KSP. Gonna basically cut throttle entirely here. Actually, it's best to have the engines on idle a bit because they take a while to spool up otherwise. Now, we lifted off at 130, so I'm gonna say that that's my minimum here. It's pretty high speed to be touching down at. Worse than the space shuttle. But better to keep things safe here. We're a bit high. Oh, no, 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 no. Wow, we've got a lot more lift than I thought. Okay. Okay, brake, 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 brake. Brake, brake. If you wonder why I don't press B continuously, it's because with more complicated situations with larger craft, that tends to lead them to break apart, as the stress of braking says, oh, aha, okay, a little bit of design flaw here. My center of mass has moved behind the landing gear. Oh, that's easily fixed. There we go. Alright, so successful flight, and with that, I'm sure there's a lot more to talk about when it comes to aircraft. We haven't even brought one into orbit yet. So, yes, but we'll leave it here for now, and let's turn to career mode and the moon. Alright everyone, let's talk a little bit about optimizing rocket stages. Now, we're not going to be able to do this ideally within KSP, but I'll show you basically what is involved, and we'll work from there, because we need an optimal rocket in order to get to the moon, at least on a lunar flyby, let's say. So, first things first, we're going to have a capsule with a parachute, and we're going to assume that we're not going to bring anything else for now. And we'll see how good we can get with that. We're not going to have the parachute bear the mass of any other stage, So we can have the decoupler here. And so what our current mass is, and I've got note. This is the other mod I have. I have a calculator and I have notes, and that's purely to show you what the heck is going on with my calculations here. So we've got, let's say we'll call this. This is stage 2, okay? And stage 2 equals the parachute 0.1, the capsule 0.84, and then the decoupler, which is 0.05. And that's pretty close to just being 1. It's actually 0.99. But let's just call it 1. And so that's 1 ton. And now the question is, how much fuel should we have if we're using this engine? Okay, so let's just have a temporary fuel tank here. But really, this is going to be X amount of tons of fuel. Now you note that this is 2 tons of fuel, and the mass of the tank altogether is 2.25. So actually there's a 0.25 empty mass to the tank. You can see 0.9, 1.1, that's 2 tons of fuel, 0.25 mass for the tank. So if we use X to be, and sorry for the math folks, but unless you really want to compute this out mathematically, you don't have to do this. I'm just showing it to you just in case you might want to. But if X is the amount of fuel that we're carrying in the second stage, then we've got 1.125 times X, where the extra 0.125 is the empty mass of the tank. All of the tanks in Kerbal Space Program, with only a couple of exceptions, have 1.125 as the multiplier on X. So X is the amount of fuel in the stage, but we also have this engine, which is 0.5, so we can add a little 0.5 there. Okay, so that's the mass of our second stage. That's it. We could add more mass by having instruments and all that stuff, but for now that's sufficient. And then we've got a first stage, which is going to have the whole mass of the second stage, plus a decoupler, which is 0.05, plus some other, fuel tank. Let me just put one here for now. And then plus an engine, right? And this is the only engine we have, LVT-30. So what we're going to have is the second stage. Decoupler was 0.05. This is 1.25, so it's 1.3 altogether. Plus 1.3. Okay, and then plus 1 times y, which is the mass of the fuel we have in here. So now we've got 2 variables, and actually 3 variables. The delta V is the variable that we're trying to get the optimal amount of, right? We're trying to maximize the delta V. And we've got 2 extra variables. And the whole delta V equation will, let's just write out the delta V equation for stage 1. And you'll see what it is. So delta V is equal to, and we're going to use the sea level ISP here, 320. So 320, and times our favorite 9.81, and then times the ln of stage 1's total mass divided by, and we've unfortunately got nested parentheses here, S1 minus Y. Okay, so that's the equation for the delta V for the first stage, right? It's the mass of the first stage divided by the mass of the first stage minus the fuel, right? And the fuel is Y. So there you go. And then if we wanted the delta V of the second stage, you'll see that, so we'll have the delta V of the first stage, yes, we can, let me just write it out, heck, jeez. And we'll use the vacuum ISP for it because it's going to be in space most of the time. Okay, and so you'll see what it looks like. It's just like that. Very similar, and so that's the form of the stuff, and you can calculate things out. Now the thing is, we've got 3 variables, right? We've got the delta V, we've got X, and we've got Y. So we need some constraints, and we just summed these 2 together, by the way. So the total delta V of all this is these 2 added together. But we need some constraints, and actually we've got some constraints. Now normally the first constraint is that the thrust weight ratio of this has to be 1, but we don't have to worry about that because the game has given us a constraint that we have an 18-ton limit. So, stage 1, which includes the mass of stage 2, right? We added that in here, has to be less than 18. So what we would do with this is, for instance, use a solver program like Microsoft Excel, though the solver in Microsoft Excel is a little bit hard to find. But Microsoft Excel could solve this for you and give you the numbers for X and Y that would be ideal. And you could look up a solver in Excel on the web and try and find out how to do that. But with Kerbal Space Program, I guess right now, since the tanks are sort of in discrete sizes, we don't have an infinite variation in the tanks. We could just guess and check. Guess and check would be fine. We don't have to go through all of this numerical analysis in order to figure out what the optimal will be. And so let me just step off to the side and do some guess and check, and I'll be back with you with the result. Okay, did I say guess and check? Well, forget about that. Let me just show you how to do it in Microsoft Excel. And so what you do is you create a spreadsheet with all the data that we were talking about. So fuel in this column, mass is calculated exactly like I showed in the notes in KSP. Oops, don't do that. So once again, the raw mass and then 1.125 times the fuel, and same thing for the first stage, except that you're adding in the mass to the second stage. And then delta V is calculated again, ISP, specific impulse, times 9.81 times the natural logarithm of the total mass here, divided by the mass minus the fuel. And same thing for stage 1, and then add these two together and you get the total delta V. Now, what's the benefit of doing a spreadsheet? I know, it's ridiculous that you're going to go to the spreadsheet thing, and in fact, what I'm going to show you is that you don't need to do this, but I might as well show you how to do this just in case. But in Microsoft Excel, there is a somewhat hidden function called solver, which is insanely important and useful. And if you don't have this showing up in your Microsoft Excel, you might want to find out how to display it. It should come with it, and so it should be right there. Anyway, you set the cell that you want to maximize, in this case the total delta V, and you set to max. You go with changing the cells for fuel, and so these are the two cells I'm going to let it change. It's not going to change anything else. And then I've got two constraints here. Let me get rid of this constraint because we only talked about this one. And so this is the constraint that the total mass has to be less than 18 tons because that's the thing that the program told us. So that's the constraint that we set, and let's have it solve it. And there we go, we're going to keep the solver solution, and we see that it puts 6.34 tons of fuel into the second stage, and then 7.16 tons of fuel into the first stage. The first stage delta V is 1,594, second stage 5,000 for a total delta V of 6,667, which is more than enough to get to the moon and back if we're trying to get into orbit. So that's excellent, but we've got a little bit of a problem here in that the second stage is way too heavy. The boost that we're going to get from the first stage isn't going to lift us all the way out of the atmosphere and out of the pull of Kerbin's gravity. And then once we hit the second stage, our second stage engine only has a thrust of 50 kilonewtons, which is enough to lift about 5 tons at a thrust weight ratio of 1. And we've got 8 tons on it, which means it's going to have a thrust weight ratio of much less than 1. And in that case, Kerbin is going to pull it right back down again. And so we need to add a new constraint. We cannot have this mass be so heavy. And that was the other one that I had there. So I'm going to say cell reference there. And I'm going to say maximum mass for the second stage is 5, which is going to give that stage a thrust to weight ratio of 1. And so I go OK. And now I'm going to have it solve it. And I'm going to keep that solution. And now it puts 10 tons of fuel, 10.4 tons, into the first stage. And it puts 3.11 tons into the second stage for a total delta V of 6,431. Now we're not going to be able to hit that exactly because we don't have tanks like that. Well, we do, but it's going to be really inconvenient to put one on. It's the toroidal tank that has the 0.11 fuel. But yeah, we can can get pretty close to this. So let's keep these numbers in mind, and we will try and get as close to possible. And we'll have a fair amount of delta V, 6,400 delta V or so. Alright, so let's go back to KSP. So basically for this rocket, you really didn't need to go all the way out to XL. What you wanted to do was to get as close to a thrust weight ratio of 1 on this stage as possible. And so now, right now we have 3 tons of fuel, 1 ton of pod, and 0.5 tons worth of engine. And this is as close as we're going to get because we don't have a small enough tank. We could try to, we don't have unlocked the toroidal tank anyway. So this is as close as we're going to get to the amount of fuel that XL suggested, but all we really needed to do was get as close to 5 tons as possible, because we added that constraint in, and we could have done that without going all the way out to Microsoft Excel. But we also wanted to make sure that we had enough fuel on this stage, and it turns out that 8 tons is not enough. We wanted 10.4 tons, and we can probably go to 10.5, mainly because we took some fuel out from the top. Let's see if this is going to be overweight or not. It reads 18 tons. It reads 18 tons. Is it going to let me take this out to the launch pad? Okay, so well, we'll try this out. This is going to be Moon Mission 1. And we're going to get into orbit around the moon. We're going to try and do some science around the moon, and we'll see what happens. Okay, well, let's go. Heck. Alright. Here we go. Here goes nothing. Thoroughly optimized rocket. 6,400 delta V. No frills though. We don't have any scientific experiments. It's just going to be Jeb doing a crew report. Now you guys gotta get me for being so wasteful, I'm sure. But this is to demonstrate a principle, if you will. Oh, I forgot about electric charge. Darn it. Hope that doesn't hurt me. Okay, that's first stage out. Second stage is lit. Good thing we have some buffer here, because this is not going to turn out the way I want it to. We can't even select the moon or anything. This is going to be tricky. And no way to restore electric charge. Oops. Okay, so being unable to create maneuver nodes, the way to figure out when we want to transfer to the moon is simply to burn when the moon appears above the horizon. And that just happens to be the case. It's just a rule of thumb. We can calculate the reason for that at a later time. When we do interplanetary transfers, I'll explain phase angles and all that, which will show you why it is that we burn for the moon when it appears above the horizon. But for now, we'll go with that rule of thumb. And we're going to be pretty close to the burn point as we get up here. I'm not going to make orbit here. There's the moon. And so we're just going to do our lunar injection here. And we're going to burn straight for the moon here. Now I don't know how much we actually get to see in map mode when we haven't unlocked the stuff in the tracking station. So I don't know if it's going to show me whether I have a free return trajectory or not, or whether it's just going to keep that a mystery. Free return is just basically means that you're using the moon's gravity to make sure that you come back to a low altitude above Kerbal. If you go around and get a boost from the moon, you're going to end up in a higher orbit. What you want is the moon to slow you down so that you get into a lower orbit. And that will allow you to return back to Kerbal smoothly. Okay, we would be encountering the moon here. I don't know what sort of encounter we've got. Can't target it. Just got overburn a little bit. We'll definitely fly by the moon now. And I guess we'll just have to find out how it goes. Electric charge is an issue. But Jeb is not worried, I assure you. Jeb is not worried at all. Can't EVA him. Haven't upgraded the astronaut complex for that. Alright. Let's head out. Obviously, as we come closer to the moon, this is the slow part of our orbit. And so we're slowing down here. As we approach... here we go. Moon sphere of influence. Now, we're on a crash course for the moon. That's not what we want. So, we want to have a radial burn away from the moon. Let's see. That's the right way. Oh, still crashing. Okay. Ooh, that's a little bit close. That's a nice periapsis right there. Okay, I'll take that. Okay, let's begin our burn to make orbit. Now remember, making orbit doesn't cost too much. Let's bring it even tighter. Okay, that's good enough. I'm not going to try and circularize. We need to make sure we can get home. Let's do a crew report. We don't have antenna on here. I didn't slap one on, so I'm just going to keep data. And we've made orbit. We just need to make sure that we get back home. We've already made the cost of the mission back, so that's good. Now, going in this direction around the moon, so if you're going in the opposite direction, we would burn around here in relation to our orbit. So this is the orbit of the moon is going this way. If we were going in the opposite direction, we burn here. Going in this direction, which is clockwise, we are going to burn around here, around at 1 o'clock. So in relation to the moon, it's around 11 o'clock for the burn if you're going retrograde, and then 1 o'clock-ish if you're going... wait, did I say retrograde? Anyway, if you're going counterclockwise, 11 o'clock. If you're going clockwise, 1 o'clock, in relation to the moon's own trajectory. Alright? And if you remember, prograde increases your speed, and that's what we want to do to pull away from the moon's gravity. We did a retrograde burn in order to get into the moon's gravity because we wanted to slow down. We were going too fast for the moon. And in this case, we're going to want to speed up to get into a trajectory towards Kerbal. Now, without any additional data, it's going to be hard to see what kind of trajectory we end up in, and that's going to be a big problem. That's why I wanted the fuel surplus. So we just line up with the prograde vector. We should be pretty close to the burn point, maybe a little bit further along will be best. Okay, prograde vector. Burn. And you can see orbit expanding. And that's escape velocity. But we don't want to go too much further than that, otherwise we'll be escaping the whole system. Really don't like the way this looks. But let's go out there. curve and sphere of influence. This is a huge bit of suspense for me. Okay, our periapsis is very high here. This is tough. Trying to do a burn here is not where I want to do it. I'd rather do it over here, obviously. Well, you know what? We could wait. There's no reason why we can't wait. Uh-oh. Don't do that. I don't want to go back to the moon. So we're just going to go around. And we're going to burn from apoapsis, which is the better thing to do. And I'm going to aim for 30 kilometers. That'll definitely bring us down. That's good enough. It may not bring us close to the KSC. May do, may not do. I don't have a time on this orbit right now. Could calculate it, but I'm not going to bother. If we knew what the time of the orbit, we wouldn't be able to adjust it very much. We don't have much leeway here. We've got a lot of fuel actually though. So that's good. That tells me that we can do much more interesting missions further on. Carry some goo containers, carry some science juniors, that sort of thing. So we've got the extra fuel that we need to carry some science with us. Okay, it looks like electric charge wasn't too bad off. That's good. I wonder if we can just bring this whole thing down without decoupling. It saves some cash. We'll see. If I can use some of the fuel here to make a soft landing and keep it all together, that would be great. Hopefully we'll get over here before it brings us to the ground. I want to pass all this highland stuff. Okay, I'm gonna turn SAS off and deploy the parachute. So in the next episode I'm gonna have to try and get this EVA report done, because otherwise we won't be able to pick up additional contracts. And that'll be good practice for us to eventually try and land on the moon. So we're gonna practice landing on the moon by landing at this location at MacTree's Belt. And that will be the plot. Okay, parachute deployment confirmed. It looks like the ground is at about 100 meters. So I'm gonna wait until we're a little bit closer before running the engine to try and slow us down. We want to get below 6 meters per second, I think. And I'll put SAS on. Okay, got us balanced on the tail. Alright, let's recover the vessel. Alright, clearly excellent work from Jeb. We got the crew report and the points for recovery of a vessel returned from orbit around the moon. And we've got our... well, we only got 560 funds back? Wow. Because we were like on the other side of the planet from the KSC. Only 17.5% despite our best efforts there. Oh well. Well, anyway, the important thing is we got Jeb back. He got 3 experience points. Amazing. And of course, we managed to get into orbit around the moon and return again. And hopefully you enjoyed that. You know what we're going to do in the next episode, so tune in for that. And if you have any questions or comments or suggestions, please do mention them in the comment section below. If you did enjoy this video, please do press like. And with that, I'll see you next time.